Alright, welcome back to another video by Firestarter Graphics and Engineering. Today we're going to do some more CFD, but today's going to be advanced CFD. We're going to do some high Mach number testing and then going into pair view and viewing the, what do you call it? The flow vectors, what it looks like visually. There we go. I don't know the real name. I do, but I keep forgetting it. Anyways, so let's open up Ondsel or FreeCAD and let's get modeling. So the first thing first, when you open up a model, I just opened up a step file of the rocket last time. Sometimes it's either zoomed way far away or zoomed pretty far in. So just hit the home key. You know what, let me get in my window, hit the home key, and it'll realign it. So I need to rename some things here. We're going to rename this one the rocket body. Now I'm going to discuss some major errors and bugs that I have found in the last few days that happen when you don't follow a certain process or standard of doing CFD, and some issues that happen. Now don't worry, this happens with ANSYS as well and other software. This is not just a Ondsel or FreeCAD issue. Things happen in every software. It's learning how to navigate those issues. And it's not a bad thing, it's just, you know, things happen and we have to figure out why. So no software is perfect. Okay, so I went ahead and renamed each one of these pieces accordingly. I'm just going to rename this as full rocket. However, I did report them in the bug finder for Ondsel just in case there is an issue and it is a bug. I think one of them is, and I'll discuss that when we get there. Okay, so we've made our rocket. Now let's go to the part workbench, and we're going to drop a cube in here. We're going to right click and do rename. This is going to be called the flow cube. Now we're also going to talk about some other stuff. So I'm going to change subjects real quick and I'm going to show you something. Okay, so one of the things I had to do for my master's project was write a 50-page technical report. I mean, that's not a lot of pages, but it's enough to learn some things. And I went through in the appendix all these calculations, how to find drag, your coefficient of drag, based off of the geometry. Now, I did not come up with these equations. These equations have been used for quite a while. They're actually done by three gentlemen. Two of the names I can't pronounce, but one of them I can, and that's James Barrowman. And he and these three gentlemen came up with these equations based on geometry and ratios of like body tube length to its diameter, the surface friction based off of the type of finish you get, you know, soft paint, not soft paint, smooth paint, rough paint, no paint, you know, what kind of surface friction you have. And then they related that to the Reynolds number. And then doing thousands of hours of testing with wind tunnels, they were able to create charts that show, hey, if you have this ratio and this dimension and this number, match it with this chart, and this is what your drag for this component is, your coefficient of drag. So I can supply a link to this paper I wrote, and I do give them credit. A really good paper I've talked about is the TR11 aerodynamic drag of a model rocket. A lot of these numbers and processes come from that, and then some of it's stuff that I've just done myself, you know, using basic physics. I don't want to use the word basic physics. Taking physics from like physics 3 and 2, all the calculus and differential equations, and then breaking them down into and simplifying them to algebraic expressions so that anyone can do them. That's what I mean by basic. It's not to belittle anyone. So let's go to the stuff about, so if this is our rocket, for example, this is just a basic rocket that I modeled in OpenRocket. You know, you can see the motor, the CP, the CG, all that fun stuff. And somehow I got dimensions, and I don't remember how I did that. If I did that in OpenRocket or somewhere else. It's kind of cool that I did that. That was a long time ago. Anyway, back on track. So equation 19 is the coefficient of drag of the nose cone plus the body tube. And this is the equation that these three gentlemen came up with. And then you have to find what SWSBT is. And this is a ratio. And I go through, and so does the TR11, the entire process of it. And then you get to the chart for Reynolds number based off of temperature, launch conditions, and then you use that to find your coefficient of friction, and then you use that with this chart, and you go through all these charts with your model rocket or your high-powered rocket or whatever you're designing. It can work for big rockets too. And you go through this entire process. And at the end, you get let's see, combining everything, we end up with a 0.596 as our total coefficient of drag. Now in open rocket, I went through and ended up with a 0.54 in open rocket for the same model. So not bad. I think that's what I ended up with. Anyway, yeah, you can it's pretty cool what I've done and what others have done and just sharing this knowledge. So I'll provide this link. Okay, let's get back to modeling. You probably don't want to sit here and look at all these equations. Okay, so now that we have our flow cube and everything set up, not set up, but at least placed in there, let's position it correctly. We know it's going to be negative 500, tab, negative 1500, negative 1500. That's going to position that cube, but now let's do its actual length of 8,000 millimeters, and then 3,000 and 3,000. And zoom out a little bit. You can't see the rocket, so highlight the flow cube, V for view, T for transparency. You can now see the missile slash rocket slash projectile inside of our flow domain. Perfect. Okay, so let's make these two a compound, and we're going to do that. And then we're going to drop another cube, and we're going to right click, rename this to refinement, and then let's go ahead and make that 1500 millimeters by 500 by 500. And then let's position that in the correct position. Everything here is negative 250. And that should place it, so view transparency. That should place it right in the center. Perfect, we're looking good. All right, now everything, at least this setup should be decent. So let's move to the CFD OpenFoam workbench. Now this is where things get a little tricky. There is a correct process, at least for Ondsel Engineering and FreeCAD, to get it to set up correctly without it throwing weird errors. Now in FreeCAD stable version, I've been able to kind of just bounce around and it's worked. But with Ondsel, since they are new, they're still refining everything. And so I've reported this issue to them and they are working on it. And so eventually, pretty soon, hopefully in the next couple weeks, there'll be the freedom of to create your boundaries first and then your mesh versus create your mesh then your boundary. However, for today, and even in FreeCAD and other documentation I've read, it's always best just to kind of make the mesh first. So, and I'll show you what I mean by that. But first, let's drop this analysis container and let's open it up. And let's go one step at a time. So physics model, we're going to use steady, single phase, high Mach number with RANs. And everything else should be default, so we're doing good. This will automatically trigger OpenFoam to use the high speed aerodynamic solver, or HISA, H-I-S-A, rather than simple foam. So now the fluid is not incompressible anymore, it is now compressible. And as we increase our velocity, you will see those effects in ParaView. Alright, fluid properties. One thing with FreeCAD and Ondsel that you have to do is switch it to custom and then back to air to make sure that, because the material properties for simple foam air is different than HISA air. Then hit OK. Notice it moves from fluid properties to air. I'm going to hit refresh. Initialize fields, do not worry about that right now. We're going to click compound and we're going to click mesh. Then we're going to go ahead and type in 100. Actually just 10 for me because I already had the 0. We're going to hit close, highlight compound mesh, drop a mesh refinement, open this up, make sure it's volume refinement set to 0.5. Scroll down, select from list, grab the refinement cube, hit solid, hit OK. Notice everything has disappeared. Select compound, hit spacebar, open that up, full rocket, rocket body, fin can, and you can go ahead and leave the flow cube hidden. We don't need it unhidden for anything. Okay, first volume mesh refinement done. Let's do the second surface refinement. So compound mesh, drop in a refinement surface, 0.1 just like last time, and then select from list. We want our rocket body and our fin can, and then we're going to hit OK. Alright, now we have our two meshes. Okay, let's now move to adding boundary conditions. So we select this face and we hit boundary condition. Set it to inlet, uniform velocity, scroll down. Now notice mine says compound face 44. Yours needs to say something similar, at least compound. If it says flow cube, you'll run into two different major errors. One will be a topological error where it says the face is out of bounds. When you go to initialize fields and you set it to inlet and you do other things, it's going to throw an error and it says, hey, it's out of bounds. I can't link to it. So make sure it says compound. Now in FreeCAD, as soon as you click this, it's always going to be compound. But in Ondsel, for some reason, you get random chances of it selecting flow. Now it's most important that the inlet is set to compound. The other ones, not so much. Alright, so at least it's compound face. I'm not even going to worry about anything else. I'm going to leave it at that. We're going to change the flow to 210 meters per second. The other error, sorry I forgot to mention the second, is as soon as you put in the reporting function to find forces, all your forces will be 0 because the flow cube is not what is being meshed, it's the compound. So basically it's going through nothing there. And it's like, hey, there's no forces here because nothing's here. So okay, hit OK. Grab the back end. We're going to do an outlet, static pressure. Now come down here, notice it says compound face 45. We're good. Yours might say flow cube, which would be okay. It'd still work. But try to grab it to make sure it says compound. And on Ondsel, it's a little tricky, but in FreeCAD, it should just be immediately. I was reading outlet at the same time. And it should just be compound. Now, this is the thing that I reported to Ondsel, and they're in the process of working on it. Okay, we're going to hit OK. Now, let's do the walls. Okay, hit the boundary condition, wall, no slip, and luckily they're all compounds. I think what happens, this is just a theory, notice when, let's actually first hit OK. Remember when we had to unhide everything and I said leave flow cube hidden? Sometimes I unhide it and then I'm like, no, I'm going to rehide it, and then I rehide it. And I think doing that causes some sort of issue because one time I've unhidden it and I noticed it kept grabbing the dang faces of the flow cube instead of the compound. So I went and I'm like, oh, hey, it's not hidden. So I hit it, refreshed everything, but it was still doing it. So I think it's the mere fact of unhiding it, and even though you would immediately rehide it, that it causes some sort of something in Ondsel to link it. Okay, sorry for that pause. I actually went and reported that bug of unhiding the flow cube and then immediately rehiding it causes the issue of where it's either randomly selecting the flow cube face or the compound face. So let's see, where are we at? We have the wall. Okay, the last inlet, not inlet, the last wall we need to make, of course, is the rocket wall. So click here, it's a wall. We're going to select from list, it's going to be the rocket body and the fin can, and we're going to hit A-OK. All right, so far, and I'm just leaving it as wall 001. We know what that means. But you can always rename it to a rocket wall. Remember, no spaces, or it'll cause it to freak out in FreeCAD and Ondsel. That's just a default thing there. They don't want spaces in the name. Okay, let's add a, what is that, reporting function. Let's go to wall 001. Let's put this at 28,000 now. Why 28,000? Because dynamic pressure is based off of velocity. So when you calculate with your air density and your velocity now, which is 210, you get 28,000 kilopascals. 28,000 pascals or 28 kilopascals for the reference pressure. We want it to be calculating the force. Go ahead and hit OK. And let's see, I have everything. Finally, initialize fields. Double click. Velocity, we want to use it from the inlet. Now, because it's not potential flow anymore, it's not incompressible, it's now high speed, it is now a higher Mach number, so focus everything from the inlet. At least for that. For pressure, let's do specify value. We're going to leave it at 100 kilopascals. Thermal used from boundary inlet, and the turbulence used from inlet since we set it to RANS. Hit OK. Refresh. Okay, compound mesh. Let's write the mesh case. Looking down here, looks like everything's written and it's OK. Let's run the mesher, make sure there's no errors. So far, so good. Now you could view it in pair view if you want to, but we've done enough of it, we don't need to. I'm going to hit close. CFD solver. I'm going to run it with 8 cores for me. Then I'm going to refresh it, double click it, and we're going to hit write, and we're going to hit run. And let's just see what happens as it begins. It should show the reporting function and the residuals. And let's just check to make sure that the forces are not 0 along the x-axis. Okay, so we're in the residuals. Let's go to reporting function. Oh, perfect. Okay, so we jumped up. I can't see, but I'm guessing 500. And now we're going to start hopefully dipping down. Yep. Okay, it should finish. The last time I did this, it finished in about 450 iterations. But we'll stop it here after about 250. It actually levels out. So that's a decent place. So I'm going to go ahead and pause the video and then actually let's stop it now, because I know what the numbers should be because I've run this test 100 times. Okay, and everything looks pretty stable, at least for forces. Residuals, you should probably, yeah, they need more time to stabilize. Anyway, but for the forces, what I want to look at is actually, no, let's just let it run. I will be back. Okay, I let it finish, and you guys remember how you can read the chart and see, sorry about that, spam call. You could see the forces. You can add them up, or you can go to edit. Yeah, I stopped it early because I already have all the information. Post-processing, reporting function, 0, forces.dat, right-click, edit with notepad, scroll to the very last iteration, and it's supposed to be 231 newtons, but 238 after 63, but after 450 it was 231. So remember, it's times 10 to the second, scientific notation. So knowing that, you can go to you can either calculate it yourself or use a calculator online, it doesn't matter. Putting in the information, the frontal area, remember, not surface area. That was one of my biggest problems when I first started CFD. I was like, surface area, and I just kept forgetting frontal area because it's what the rocket's moving through. And then you can see that it's 0.91, and then in pair view, this is what we get for our visualization. So let's go ahead and actually do this in pair view so you can be like, oh, that's kind of cool. So let's do this. I'm going to go ahead and open PairView. Now, anytime I'm on a form, I like using Google Docs or Microsoft Word, inputting my equations just to show things, and then a picture, and then I post that. And it's really kind of cool. Just an extra way of presentation. Okay, so remember, I don't like opening up PairView right after it runs. I like directly opening the case file. So I already have it saved. Oh, whoops. Go here, the PV foam. Remember, it's under case, not mesh case. Mesh case is obviously the mesh. So hit OK. Let's see, decomposed. And we want patch wall 001 since that's the rocket. And the internal mesh so that we could do stream chasers if we wanted to. And we're going to hit OK. It should bring that up. Now, first, let's do a filter, common, extract block. Let's bring out the rocket, hit apply. So now we have, whoops, wrong button. What the heck? Oh, it's not like FreeCAD and Ondsel. Okay, I keep forgetting that. Let's reset my view. Let's go that one. Okay, so go to the last timestamp, and we can change the surface to surface LIC, change this to the velocity vector. Doesn't really show too much, so I'm not going to worry about that. Let's just bring that back to surface. Okay, so how do we get the other thing? Let's open up our block, unhide it, so everything's hiding again, and we're going to hit this slice button right here, and we're going to slice against the Z normal. We're going to hit apply, and now I'm going to hide the plane, because if you don't, you can end up messing it up trying to view things. Okay, so on the slice, I want to show the velocity filled. Okay, so you can kind of see how that's looking. I don't know if this is just visual or if that's beginning to be a shock wave. So let's do this. Let's change the color, and we're going to do rainbow desaturated. Hit apply, close this. Okay, yeah, that went away, but you could see shockwave starting to, I'm guessing this is a shockwave starting to appear right here. And then you can see the wake left behind it. And if you wanted to, with the slice, you could go to surface LIC and then switch the color mode from blend to, I think I missed it. Nope. Blend to multiply, enhance contrast, color only. Takes a lot more rendering power, but it's a cool visual. But I think in this case, even points, that is cool, but I don't like it. I think surface is a really good visual representation. If we go to the extract block, I like setting this to omega because it's kind of cool to see the different colors, but we could also set it to velocity or solid color. But for me, I'm going omega. Okay, so that's today's video. Nothing too crazy, but more advanced. Now we can do the same thing, and as we increase that velocity, so use the exact same model and then increase the velocity to a lot higher. Let's say 420 meters per second. So as you increase that, like I said, to 420 meters per second, visuals are going to change. So I paused the video, went ahead and did that, and make sure you change your reference pressure or it won't work. So I went ahead and took a picture of that, and you can see right here how things are changing. You can see this separation now. Look at that. I don't know if it's really separation. You can just see how the flow, and especially right here, you probably, I think those are vertexes. I'm not zoomed in, but it's just pretty cool. Start seeing how things work with high speed. So, all right, that's today's lesson, and that covers some advanced features in the CFDOF workbench. These videos should be enough to get you going to analyze all your rockets. Now, what you can do is once you calculate your drag, go ahead and use your geometry values and test out the hand calculations in my document right here, following this appendix, and they're the same ones in the appendix of TR11. It's the same process. All I did was used it as a reference in my paper, and I did an example based on one of my rockets showing, but it's the same process. And see what you come up with hand calculations using the same velocity, because once you get all of your coefficients of drag, remember, things are going to change based on velocity. So once you start, like this is 0.6, notice we didn't use velocity whatsoever in the geometry equations. You can go back, change velocity somewhere else to get values to replug back into here and see what your hand calculations go up. I highly recommend learning how to do it by hand just to reinforce everything, and I highly recommend reading all 50 pages of that TR11 tech report from Estes, or Estes, however they say it. Because once you do that and go through it, you just feel really accomplished. And then when you add it with the CFD, and then when you add OpenRocket on top of this, it just works great. And OpenRocket is phenomenal. I love OpenRocket. I would never choose OpenRocket over CFD, and I would never choose CFD over OpenRocket. They should both be used. OpenRocket tells you so much stuff: the apogee, the burnout time, the velocity off the rail, the best time for your ejection charge for your parachute, all the stuff. It is basically CFD numerically. It just doesn't have all the visuals. It just does iterations just like CFD does, but doesn't produce any of the visuals of what is the flow doing. It just gives you your coefficients of drag and everything else. I mean, I love OpenRocket. So anyways, thank you for watching. I hope these make sense, and good luck with all of your CFD. And if you have any questions, feel free to ask. I highly suggest following some Facebook groups such as the High Powered Model Rocketry, the Open Rocket, the 3D Printed Rocketry. That's a really good group where you can learn how to fully 3D print an entire rocket for high powered, not just model rockets, but we're talking extreme high powered rockets. So check it out. Anyways, thanks guys, and have a great week.